And we're going to talk about Coulomb Mohr theory for ductile materials. Okay, so far we have seen two more theories, right? Maximum shear stress theory and distortion energy theory, and maximum shear stress theory is the more conservative of the two. Coulomb-Mohr theory is slightly different in the sense that it's to be applied for ductile materials when the failure in compression is different from the failure in tension. So the previous two theories, we assumed that the, the stress for the strength of the material in compression is the same as strength in tension. So this theory is applicable for ductile materials whose compressive and tensile strengths are different. So one way this will manifest is you'll be given different strengths, and then you'll know that it's the theory to apply. So what is done is so previous to theories, we wanted to find a strength, and the strength was found by a simple tension experiment where you keep loading the material till it fails, and that is the strength. In this case, you need two tests. You need a test for tension, stress just like the previous one, and you also need a test for compression. And so we need two tests to perform two tests. Okay, and these are tension and compression tests to find the tensile strength ST and compression strength SC. So the simplest way you can think of this is, well, you need that specimen I drew with that gauge length and so on, but the way we analyze this is we draw this small cube element and then we show the stresses. Right, so this is the stress when the material fails in tension, and then you can draw a similar one for compression, where now the arrows are pointing inwards. One second. Let me just change something here in mind. Okay, so what we'll do is we'll draw the question. Yeah, what would cause the material to have a different discussion? Is related to the material properties of the of the substance. Like for example, when you look at reinforced concrete, it can only bear compression. It cannot work in tension. So you'll never see concrete being used for other things. So it's really the microstructure which is sort of beyond the course.
I mean, I understand that for brittle materials, but you said specifically
Ductile. This is empirically observed that some materials do have, and I'm pretty certain it's the microstructure. I think some nickel alloys have that. Not all of them, but some do. But yeah, so that's sort of I would say beyond this course, but it is to do with the microstructure, the way the material is oriented, or the grains are oriented within the structure. That's a good question. And I would highly suggest that you read about it, search for it and read about it. Let's not digress over here. Okay, so what I'm going to do is I'm going to draw Mohr's circle for both those cases. So we know if we have a tensile specimen in tension, then the stress in the x direction is st, the stress in the y direction is 0. So we can draw, and then clearly the shear stress is 0. So when we draw these points, that for this particular element, the first one on the left, I would have a stress of 0, which will be the origin, and then there'll be st on the x-axis. So I'm going to draw a circle now. And it's slightly bigger. Just change the ST. And then the same thing can be done for compression, but however, now the circle would be on the left side because SC is negative. So circle. Okay, now I randomly drew this circle to be bigger than ST, and that only happens when SC is greater than ST. You have materials where SC is greater than ST. You have materials vice versa. ST is greater than SC, and so that's not an issue. You should just draw the right circle. So this is minus SC, right? Where SC is, in this case, the value would be positive. Okay, so what I can do now is I can draw a line which is a tangent to both these circles. And I can basically, I'm going to just highlight the region which is within the two circles and those inscribed lines. So what this theory says is that once you have this envelope, these lines, this is called the failure envelope, and there is no failure in the yellow region. So things will not fail there. So you need to find the envelope, and you're within that, things are not going to fail. So DCM predicts no failure in the shaded yellow region. Okay, so now we have this that's the theory. Now the question is, we have to use this theory in our problems, right? How can we come up with failure criterion from that theory? So what we're going to do is we are going to find an equation for this envelope, okay, for any random stress, and then use that to derive equations. That is this figure. So let me get to that. A little bit of construction here. Done. Just start copying this. Okay, let's blow this up a little bit. Okay. We did the line. Let me redraw it. Okay, so I'm going to draw another circle. So let's say that there is another. Okay, so let's assume that we are interested in finding what happens to an object or a element who has a general stress distribution as so. Okay, so we have that, and that's given to us. We need to figure out for that particular stress distribution, which has shown that plane stress distribution, will it fail or not. So the first thing you want to do is take the stress and find the principal stresses from here. Okay, so take that, find principal stresses. So let's say there are sigma 1 and sigma 2 and sigma 3, right? One of them is going to be 0, right, for a plane stress, but identify the max and the min one. So let's say this is the max and this is the minimum one. And so if you know the principal stresses, you pretty much can draw the Mohr circle for that. So I'm going to draw the next Mohr circle is going to be for this stress condition. Okay, we need to inscribe it. That circle looks good. Okay, too many circles now. Let me start naming things, and it'll become slightly more clear. So this is, say, the center of the biggest circle. So let's call that C. The suffix, the subscript C is for compression. And then let's say that the center of this one is here, CT. And then the center of the gray circle, which is a general stress corresponding to sigma 1, sigma 3, is right here. Okay, what I need to do now is draw normals to this tangent. So just connect this so that this is a 90 degrees angle. This is probably a little off. I didn't want it here. Just put it here. Okay, just there's a slight error in my figure, but assume that it is 90 degrees is actually is the tangent there. So CC. Okay, let's name these points. Let's say that this point is B subscript C, this is B subscript T. Okay, now let's say that these radii are, say, R3, R2, R1. That will make our life easy when we do the math. And then the last thing we'll do is identify these centers. Okay, what are the coordinates of the center? So centers CC you can see that the center CC is going to be half of SC, right? Because SC is the diameter of the circle. So it's going to be minus SC divided by 2, the x-axis, and 0 for the y-axis. For CT, you can see that it's the half of the diameter of the smaller circle, ST, whose diameter is ST. So this is going to be ST divided by 2 for the x-axis and then 0 for the y-axis. Okay, and the last one we need to figure out is CC, C. So this one is going to be, well, we know that the principal stresses for the gray circle are sigma 1 and sigma 3. So clearly this is sigma 1, this is sigma 3, which is the smaller of the two. And so the center of the circle is going to be the arithmetic mean of sigma 1 and sigma 3. So sigma 1 plus sigma 3 divided by 2, 0. Okay, so I just need to join those two red lines so that I get the meeting point of those lines. So just extend that. And this one. And they actually, both of them should meet on the x-axis because that is, they're basically inscribing a circle and they're symmetric. So let's say this point is O. Okay, let's write down. Well, I think I've written down the centers, but these radii are easy to figure out. The radii can be found given that we know what the principal stresses are, right? Principal stresses are S.
Sigma or gamma?
Gamma. There's no gamma anywhere here. Oh, this is, sorry, R. This is the radii. This thing. So R. So the radius 1, you can see, is the half of ST, and then R3 is the easier one, right? It's the half of SC. Okay, what does the middle circle represent? So middle circle represents the generic case whose stress you want to find. So let's say that you're given an element or a machine which is acted upon by stresses. You identified the critical point, you found the stress in the critical point. this is that particular figure for the critical stress. So then you find the principal stresses and then you plot it on the Mohr circle. So clearly, if this gray circle is within that polygon, then you're good. You won't have a failure. If it's outside the polygon, then you'll have failure. So we are just trying to find a critical condition to which you'll get a failure. In this case, it's just sort of touches the red line at 2 points. Anything less would be good. Anything above that, crossing that red line would be bad. But we are trying to find the boundaries. That's where we're going. Okay, but that's a good question. I think I did not quite say it clearly. So then we can write R3, which is the radius of the biggest circle. It's SC divided by 2. And the last one is R2. Now, the radius of the smallest circle, and this is something we've done before, is if you know the principal stresses, the radius of the circle in terms of the principal stress is always sigma 1 minus sigma 3 divided by 2. Or you can see it from this construction. It's basically the distance between sigma 1 and sigma 3 divided by 2, right? Because sigma 1, sigma 3 sit on the diameter. Okay, so with that, we are almost ready to start finding the condition which we'll be using. Need to copy this down. Okay. Okay, so okay, now we're ready. Now that we have everything on paper. So the math is not too hard, but the figure is kind of involved. So what we see is that the triangle OCTBT, triangles OCTBT is similar to OCB and OCCBC. So they're all similar triangles, right? So sort of you can take that and blow it up a little bit, OCTBT, and you get OCB. So if that's the case, then the ratio of their sides, corresponding sides, should be should have the same ratio. So what we can do is write down OCT. So that's this size divided by BTCT, which is this radius, equals OCBC. So the same corresponding side. So you can see in the numerator, I only have OCT, and I also have OCC, and then BCC. So that ratio equals alpha. Okay. Okay. Eventually, alpha will not matter. So I'm going to rewrite this equation as 3 equations. So OCT is alpha times BTCT. So just take this part and the alpha, equate them, and then simplify. Similarly, I can write OC as alpha times BC. Okay. Now what I can do here is I notice that OC can be divided into 2 parts, right? There's OCT and then CCT. The sum, so the distance from here to here is distance from O to CT and CT to C. So this is OCT plus CTC equals alpha BC. Okay, then OCC, which is the third part of this equation, is alpha times BCCC, and then I can break down OCC as OCT plus CTCC equals alpha BCCC. Okay, so let's just call that 1, call that 2, call that 3. So what I don't want is I don't want OCT because I don't have a actual, I don't know the location of point O, so I really don't want that to show up in my equation. So what I can do is I can eliminate OCT, which is now this part, simply by subtracting these expressions up, right? So I can do 2 minus 1, for example, and I'll end up with CTC equals alpha times BC minus BTCT. I can also do 3 minus 1. So 2 minus 1, 3 minus 1. And I would have, so CTCC is this part equals alpha BCCC minus BTCT. Let's call this 4 and call this 5. So the other thing which I'm not interested in this is that alpha. The alpha is just a factor which I need to get rid of. And so it's easy to see that if I divide these two expressions down, so if I divide 4 divided by 5 or 5 divided by 4, alpha will go away. And that's what I really want to eliminate alpha. So let's do 4 divided by 5 on the next page. So 4 divided by 5, and I have now CCT, CCC equals BC minus BTCT divided by BCCC minus BTCT. This is not right. Hold on. Let's go back. This should be, so it's CTCC, right? Yeah, so it should be CTCC. I wrote the other one as CTC. So this is a distance. So it really doesn't matter how you put it there, CTC. Okay, so let's just, I think I have found all these things previously, so I just need to sub in the value. So CTC is the distance from the center of the tension circle. See here. So it's the distance from here to here. So as long as I know the coordinates of CT and I know the coordinates of C, so the coordinates of CT is ST divided by 2, coordinates of CC is sigma 1 plus sigma 3 divided by 2. So I just need to do is subtract the x coordinate from of this minus this. That way the sign is positive, or you can do it the other way too. It doesn't really matter. So this is going to be ST divided by 2 minus sigma 1 plus sigma 3 divided by 2. So that's the first part. Then CTCC. CT is here, CC is here. I've already written down, well, CT is ST divided by 2. CC is minus SC divided by 2. So I just have to subtract this from that. And so I can write ST divided by 2 minus of SC divided by 2. Okay, we're almost done. Left side, we have BC minus BTCT. Okay, the distance between B and C. So BC is R2. BTCT is R1 and B3, BCCC is R3. So I'll just write in terms of that. It might be easier to make it to have another step. So BC is the middle circle, BTCT is the smallest circle, divided by BCCC is the largest circle, R3, and then this one is R1. And now I already have expressions for R1, R2, R3, right? I wrote them down here. I write it down here. Maybe the previous page. Yeah, so I have these expressions. I just have to sub them in. Copy. Paste. Okay, so I'm just going to sub that in. So in the numerator, we still have ST divided by 2 minus sigma 1 plus sigma 3 divided by 2, whole thing divided by ST divided by 2 minus SC divided by 2 equals R2 minus R1. So sigma 1 minus sigma 3 divided by 2 minus R1, which is ST divided by 2. The whole thing divided by R3, so SC minus R1, which is ST divided by 2. Okay, so that is the expression which tells me how to determine the envelope, which takes into account the stress in the bigger circle, the compression in this case, the tension circle, and the generic stress case, where there's sigma 1, sigma 2, sigma 3. So it looks very complicated. It turns out that you can simplify just a very simple expression. So it's quite simple. Sigma 1 divided by ST minus sigma 3 divided by SC equal to 1 is what comes out when you try to simplify it. So it's pretty simple in terms of relating the boundary of that, the failure envelope in the case of the Coulomb theory. So just like we had these equations for MSS and D distortion energy, this is the expression we need to use. Now let's see how we can, if we can really understand these equations graphically, just like we did for the maximum shear stress, right? So let me just show that to you. So for the maximum shear stress, we came up with okay, it should be later then. Yeah, this is what we came up with, right? So the yellow part, so this is, by the way, plot of sigma A with sigma B, where sigma A and sigma B are the principal stresses. The yellow region shows you the MSS theory, that's the boundary. And then the distortion energy theory predicts the red boundary. So you can say MSS is conservative than D. Now the question is, can we do a similar plot for Coulomb theory? And we can, and I'm going to do that next. So let's analyze sigma 1 divided by ST minus sigma 3 divided by SC equal to 1 for different cases of principal stresses. Okay, so just like, and I did this in fair amount of detail for the maximum shear stress theory, and you can go and refer to that. So I'm just going to go so slowly as I went there, but you can refer to those notes. So the first case is when sigma A is greater than equal to sigma B is greater than 0. That means that sigma A and sigma B are positive, and the third shear stress is um, is 0 clearly. So sigma 1 is the maximum stress, so it'll be sigma A. Sigma 2 is the middle one, which will be sigma B, and sigma 3 is the lowest one, so it'll be 0 in this case. So then from this theory, so let's call this something, let's call it, say, star. So from the equation I highlighted, I just need to put sigma 3 equals 0, right? So if I put sigma 3 equals 0, I get sigma 1 is equal to sigma A. So it'll be sigma A divided by ST minus 0 divided by SC equals to 1. And so the criteria would be sigma A equals ST. So case 2 is when sigma A is greater than 0 and sigma B is less than 0, which means that one of the stress is compressive, one of the stress is a principal stress is tensile.
Is that like 0 above like the SC?
Yeah. So now we have sigma 1 equals sigma A, sigma 2 equals the middle stress, so 0, and sigma 3 is the lowest one, so that's sigma B. So our theory predicts that, so from the highlighted equation, we have sigma A divided by S T minus sigma B divided by SC equal to 1. So that is going to be our equation for case 2. And then the final case is that both these stresses are compressive. So sigma A is less than 0, sigma B is less than 0. So here we have sigma 1 equals 0, sigma 2 equals sigma A, sigma 3 equals sigma B. And so the equation from 3 would be 0 divided by ST minus sigma B divided by SC equal to 1, which means the sigma B will be equal to minus SC. Okay, so this is, so once you have these cases, you can now make that plot similar to the one for MSS and D. It's going to look very similar to MSS, except that the failure in tension is going to be different than the failure in compression. For the MSS, we assume ST is same as SC, and here ST is not equal to SC. So the figure will look something like this. That's ST, ST, sigma A, sigma B. And then since in this case, SC is greater than ST, you'll have something like this. So you can see the boundaries. So that's basically case 1. And this is case 2. So those are the cases where you'll have a square boundary. So then we need to join this line and then we have, this is going to be case 3, and then that one also is actually case 3. So no failure. So that's even within the boundary, you're not going to have failure. If you're outside, you're going to see failure. So now this theory can be slightly modified to include the factor of safety. All you need to do to include the factor of safety is you need to divide the strengths by the factor of safety. So adding a factor of safety n, what we need to do in this case is sub in st by st divided by n and sc by sc divided by n. And so when you do that, you have sigma 1 divided by st, right? Yeah, st divided by n minus sigma 3 sc divided by n equals 1. And so the equation would look like this: sigma 1 divided by st minus sigma 3 divided by sc 1 divided by n. If you want, you can have actually a different factor of safety for compression from that of tension, and that will do too. So what this is saying is that by having this equation, what will happen is your actual failure region would change to something like this. So that will be the factor of safety. So your factor of safety will shrink that region, so that you're going to say that you're going to be more conservative in your design. You're going to be restricted to that, not to that bigger polygon, but the smaller one. And the factor of safety is going to squish things up for you. Clearly, as n increases, that the red polygon keeps decreasing, and as n becomes close to 1, it goes to the boundaries of that failure region. Okay, one last thing, and then we are done. Now, we talked about tension and compression throughout this lecture. How do you take this theory and apply for a case where there's pure shear? So let's apply for pure shear. Okay, so in this case, we're looking at a stress which looks like this. There's only shear stress, there's no normal stress. And we want to figure out what is the failure criteria for shear stress using this theory of Coulomb's theory. So what we'll do is we'll draw the Mohr circle like we always do. So in this case, the Mohr circle will be centered at 0, 0. The radius would be tau. Okay, so the sigma 1 would be tau, sigma 3 would be minus tau. So we can write sigma 1 equals tau, sigma 3 equals minus tau. And we sub that in our expression, right? From the star expression was the one I wrote down the previous page, I think. But it's basically this expression without the factor of safety. So I can put tau divided by st minus tau divided by sc equal to 1. Now, if tau equals SSY, so we normally use SY as a subscript which tells us yield strength and shear. Then we can sub that in that expression I wrote down, and we can get, well, just move this to a new page. Okay, so I'm going to sub that in. So we have SSY, yield strength in shear, divided by ST minus is plus. So SSY divided by SC equals 1. And so if you simplify this, you get SSY, shear, yield strength in shear, equals ST times SC divided by ST plus SC. I don't know if you know this, but it is basically like the harmonic mean, except there's no factor 2 there.